Hello and welcome. This is going to be our lecture video for February 3rd through 4th. Get your notes. Let's go ahead and get started. A few vocab words. Limit. A limit is a value that we cannot directly plug into a function. The most famous limit would be infinity. That's what we use most often as a limit, but there's other examples. Sometimes we use 0 as a limit because we can't divide by 0, but we can talk about what happens as we get very close to 0. And so we can have limits as x approaches 0, but we can also have limits as x approaches infinity. And although we cannot directly plug in these numbers into certain functions, we can still talk about the math that happens as x gets very close to those numbers. All right, convergence is when a function approaches a value at a limit. All right, our most salient example of convergence is probably exponential decay. All right, so in exponential decay, as x goes to infinity, f of x typically approaches 0, or it approaches the horizontal asymptote, the k value if there is one, but typically it's 0. All right. Divergence is a function goes to infinity at a limit. All right, and good example for this would be exponential growth. Because as x goes to infinity, f of x also goes to infinity. If I continue to move to the right on this function, this does not approach any sort of value, it just goes up forever. So, yeah, the notation for this, for a limit, is you just say lim, and then below it you say what x is going to be approaching. So x goes to infinity, or x goes to 0, or any other value. And if you're going to a specific value, you can put a little plus or minus here to say if it's approaching from the left or the right. But with infinity, obviously it's approaching from the left. And you can approach negative infinity. You can put whatever you want here. Okay, so write a function that will calculate the return on investment growing at 100% annual rate compounded x times per year for 1 year. So I'm going to start with my final amount a equals p times 1 plus r over n to the power of nt. And I'm going to plug in the values that I have. So I know t is 1 year, and the rate is 100%, which expressed as a decimal would be just a 1. And then x times per year just means swap out these n's for x's. And I think that's all I can do. So now I've got final amount A equals the principal. So it's just the return. So actually I think we can just drop the principal, because if all we care about is the return, then we'll calculate, instead of calculating A, we'll calculate just our interest equals 1 plus this 1 became a 1, or this R became a 1, this N became an X, and then this N became an X times 1 doesn't change anything. So our interest will be 1 plus 1 over X to the power of X. All right. Now what happens? What is the limit as X goes to infinity of this function? All right, so you need some pretty high-level math to be able to calculate this, but you don't need very high-level math to be able to just plug in really big numbers and see if this starts converging. And this does indeed converge. The limit as n goes to infinity of 1 plus 1 over n to the power of n, so this one writes it with n's instead of x's, but it's the same thing we just wrote, is e. This does not diverge, it converges to a specific number, and what this means is that compounding infinite times per year does not yield infinite money. It is better than compounding less frequently, but it does have a limit, and that limit for a 100% investment is E. And then we can use E to scale investments of any other percentages. So E is an irrational number. That's important to know. And it's named after this famous mathematician, Leonhard Euler. Pronunciation on this name is Euler. And I have made that a test question before. You need to know how to pronounce this man's name, so you do not make a fool of yourself in a college math class by calling him something other than Euler. That's the only way you can pronounce this. All right. So E it's an interesting number. It looks like it's going to repeat because it goes 2.718281828, but then it just becomes absolutely random. 45904. And all we ever really need to remember is maybe 2.718 is pretty good. But if you can remember that 1828 pattern, you can remember a whole lot more significant digits. So that's all we need. Most of the time. All right, and if you haven't put this formula in your notes yet, now's a good time. This is how we can calculate continuously compounding interest. So essentially we're taking the idea that a 100% return caps out at E for being continuously compounded or compounded infinitely many times per year, and then we're scaling it by whatever our actual interest rate is. Remember, interest rate is always going to be a decimal, so if it's given as a percentage, always move the decimal place 2 spots. Time is always going to be in years when we're talking money. And for E, we can find that on our calculator on the second divide button, or just plug in 2.718 and you'll typically be close enough. All right, so let's practice with this. A saving account earns 4.62% annual interest compounded continuously. As soon as you see that word continuously, write down A equals PE to the RT. You deposit $500, so that'll be our principal. how much will it be worth in 10 years? That'll be our time. And with our interest rate, convert that to a decimal by moving the decimal place twice, so 0.0462. Don't accidentally turn this into 46% by only moving it one spot. All right, so our final amount A equals 500 times e to the power of 0.0462 times 10. Plug this into our calculators. And I will get our principal 5,000? No, just 500. Times, here's where e is right there, so second e to the power of interest rate 0.0462 times 10. Make sure that whole thing goes into the exponent. Use a set of parentheses if you've got an older calculator to make sure that times 10 ends up in the exponent. And we get $793.62. 793.62. So 793.62. All right. We'll call that good for this lecture video. I'll have you do a few more continuously compounding interest problems here. But have a good rest of your day.